When you observe a rocket such as the SpaceX Starship ascending into the heavens on a massive column of flames, you are witnessing the apex of contemporary science and engineering united to propel an object as tall as a skyscraper high into the atmosphere and beyond our planet. The rocket engine represents a crucial piece of technology in today's world, just as it did a century ago, and even a millennium in our history. Rocket engines have progressed alongside human civilization, and we can trace a line that follows that progression directly from rudimentary origins to interplanetary exploration. The beginnings of rocket technology date back to 9th century China. Ancient scientists were conducting experiments with chemicals such as saltpeter, sulfur, and charcoal in their quest to produce gold or halt aging. What they inadvertently created was the first rocket fuel, a black combustible powder that you likely recognize as gunpowder. Rather than manufacturing guns, the Chinese developed rockets. By the era of the Song dynasty, around the year 1000, this explosive compound was militarized into something the Chinese termed fire arrows, bamboo cylinders packed with gunpowder and fastened to arrowheads. When set ablaze, these contraptions produced sufficient thrust to propel arrows farther than any traditional bow could achieve. The crucial breakthrough occurred when the Chinese mastered the technique of controlling the explosive force of their gunpowder rocket engines by blocking one end of the bamboo cylinder while keeping the other end exposed. Song dynasty engineers were applying the identical physics that would later bring Sir Isaac Newton recognition many centuries afterward. For every action, there exists an equal and opposite reaction, meaning that escaping gases from the open end of the bamboo would create thrust in the reverse direction. These early rockets were erratic and difficult to control, but they successfully illustrated the fundamental principles of rocket propulsion that would persist into contemporary times. Throughout the Ming Dynasty period, spanning from the 14th to 17th centuries, rocket technology evolved into multi-stage configurations. The Chinese named their novel invention the waterborne fire dragon, and it was documented in an ancient military treatise as a large bamboo core rocket approximately 5 feet in height, with a carved wooden dragon's head serving as a nose cone. 4 smaller rocket engines were secured to the flanks of the body, and positioned above that was a second tier of rocket engines functioning as a second stage. Once the initial boosters exhausted their fuel, the secondary stage ignited automatically, extending the rocket's range and precision. After the second stage had depleted, it would activate a cluster of arrows to shoot forward from the dragon's mouth. This configuration bears remarkable similarity to modern multi-stage rockets such as the Russian Soyuz, and the Ming Dynasty Fire Dragon was capable of traveling over 1.5 kilometers. Despite the ingenuity of these ancient Chinese rocket scientists, they were constrained by the gunpowder fuel accessible to them. It lacked the efficiency and reliability to power a long-distance or high-altitude rocket. It would require waiting until 1903 before rocket engine technology would progress once more. A Russian schoolteacher named Konstantin Tsiolkovsky would emerge as the founding father of modern rocketry through his pioneering rocket equation. Konstantin demonstrated mathematically that space travel would demand liquid-fueled engines with high exhaust velocities. In his liquid-fueled rocket design, you would require 2 propellants, a combustible substance and an oxidizer. While many combustible liquids are available, liquefying oxygen necessitates extremely cold temperatures, what we designate as cryogenic temperatures, specifically below -180 degrees Celsius. That would have been exceptionally difficult to accomplish in 1903, but electricity was spreading rapidly throughout the world, and the necessary technology would follow swiftly. The next component you need to make a rocket engine function is a source of pressure. You must force the liquid propellants from their storage tanks into the combustion chamber where they can be set alight. Higher chamber pressures will produce a more powerful combustion force that consumes the fuel more thoroughly. The final element of the rocket engine is the nozzle. The combustion byproducts, the exhaust gas, will naturally migrate from areas of high pressure to low pressure. So the substantial difference between the small high-pressure environment of the combustion chamber and the wide low-pressure area at the tip of the nozzle will cause the exhaust gas to flow rapidly in that direction. You also require a mechanism to assist with steering, but we'll address that momentarily. Konstantin's most significant work, the exploration of cosmic space by means of reaction devices, suggested liquid hydrogen and oxygen as ideal propellants, presented multi-stage rocket designs, and promoted gyroscopic guidance systems. 2 decades afterward, on March 16, 1926, American physicist Robert Goddard would launch the first-ever liquid-fueled rocket in Auburn, Massachusetts. Powered by liquid oxygen and gasoline, his 3-meter-tall vehicle flew for merely 2.5 seconds, achieving 12.5 meters altitude. It wasn't impressive, but it represented a promising beginning. Goddard would rapidly innovate upon his design and throughout the process would invent essential rocket engine technology, such as regenerative cooling, which circulates fuel through the engine walls to prevent overheating. He implements the first gyroscopic stabilization by positioning movable fins beneath the engine nozzle to direct the exhaust plume. Goddard was also the first to generate pressure inside his engine by employing a fuel pump. So rather than depending on a pressurized tank to contain the propellant that would quickly depressurize once released, the fuel pump maintained a steady flow of propellant from start to finish. By 1935, Goddard's rocket exceeded 2,300 meters in range by utilizing modular designs with separate upper stages, just as the Chinese had accomplished centuries earlier. Regrettably, during his own lifetime, Goddard was not recognized highly as a father of the rocket engine. Instead, he was dismissed as little more than an amateur enthusiast. However, his patents would subsequently become foundations of later United States and German rocket programs. Speaking of Germany, Hermann Oberth's 1923 book, The Rocket into Planetary Space, would inspire a community of amateur German rocketeers. Among them was a young man named Werner von Braun, who was experimenting with liquid oxygen and alcohol-fueled engines that could produce far more power than any design that had preceded them. Von Braun's first major invention, the V-2 rocket, was deployed by the Nazi Army in 1944 and would become the first long-range ballistic missile. The engine burned a combination of cryogenic liquid oxygen and 75% pure ethanol, generating 25 tons of thrust, sufficient for the V-2 to reach a velocity 5 times the speed of sound. Von Braun's revolutionary design incorporated a new cooling system known as film cooling. This injects liquid ethanol through tiny openings in the combustion chamber walls, creating a protective barrier around the metal. The V-2 engine also utilized a sophisticated new fuel injection system with 18 separate nozzles, ensuring stable combustion by precisely blending fuel and oxygen streams. Von Braun also refined Goddard's fuel pump system by inventing the first gas generator, essentially, by extracting a small quantity of the rocket's propellants and igniting them in a miniature combustion chamber. The exhaust gas from the generator would rotate a turbine, which would drive the fuel pump. With this innovation, the V-2 pumps delivered 125 kilograms per second of propellant by rotating at 5,000 revolutions per minute. The V-2 engine had a burn duration of approximately 68 seconds, but that was adequate to reach altitudes exceeding 200 kilometers, making it the first man-made object to reach outer space. The greatest limitation of the V-2 design was the ethanol fuel. It was extremely difficult to manufacture. The Nazis had to process 30 tons of potatoes into alcohol simply to launch one V-2. In the wake of World War II, captured Nazi rocket technology would jumpstart missile development across the globe. The Soviet Union succeeded in obtaining V-2 hardware and design blueprints, while the Americans acquired von Braun himself and many of his colleagues. The next great advancement in rocket technology would emerge from the Soviet Union in the late 1950s. A consequence of their reverse engineering of V-2 components. The R-7 rocket was originally designed as an intercontinental ballistic missile but would discover its true calling as the world's first orbital rocket, a machine that would launch the first human satellite and place the first man into space. The engines powering the R-7 were revolutionary, a new design created by Soviet engineer Valentin Glushko. Each of the 4 side boosters possessed an RD-107 engine, while the rocket's core was powered by an RD-108. For propellant, the Soviets had resolved a critical problem of the V-2 by replacing the alcohol fuel with kerosene, which was considerably easier to mass-produce. Glushko also possessed an innovative solution to scaling up the power of the rocket engine to unprecedented levels. By enlarging the size of the combustion chamber and engine nozzle, you're simply creating a larger, hotter fire that's expelling an even faster hurricane of exhaust gas. Conditions can become extremely unstable, and even a slight bit of instability in a large engine will result in catastrophe. So Glushko divides the main combustion chamber into 4 smaller chambers, each one with a small engine nozzle. So when you combine those together, you actually achieve more power with greater stability. He also had every combustion chamber operating from one common turbo pump, so he wasn't making the engine 4 times more complicated either. Glushko also invents the vernier thruster to assist with guiding the rocket. These are miniature rocket engines attached to the side of the main engine, and they can be pivoted back and forth on a mechanism that directs their thrust to steer the rocket. The RD-107 and 108 also implement von Braun's gas generator cycle. It diverts 3% of the propellant away from the main combustion chambers to power the fuel and oxygen pumps. The exhaust from the gas generator is then expelled from the engine. This is not the most efficient design because we're sacrificing 3% of the total energy in the fuel, but it is dependable and effective. Over on the American side, the newly established NASA is scrambling to match the capabilities of the Soviet R-7. American rockets of this period were essentially just extensions of the V-2 design. They hadn't discovered a method to evolve the rocket engine like Glushko had. NASA's boosters were small, underpowered, and unreliable, but there was a space race underway, and the Soviets were winning. So, Americans deployed their ace in the hole. They brought Wernher von Braun and his former colleagues out of retirement and assigned them a new mission: construct a rocket that will transport men to the moon. And that's precisely what they accomplished. For the Saturn V moon rocket, von Braun and his team would construct a behemoth, the F-1 engine. It remains to this day the largest and most powerful single-nozzle rocket engine ever flown. Von Braun wasn't interested in adopting Glushko's multi-chamber approach. He was going to construct one epic combustion chamber with a nozzle so wide you could park a Jeep inside it, and then he was going to attach 5 of these engines together to create the Saturn V booster. In early hot-fire testing of the F-1, the engine would violently destroy itself. This was caused by powerful oscillations in the exhaust gas, waves of air pressure that would push and pull on the nozzle wall. It's comparable to how an opera singer can shatter a wine glass with their voice. So the greatest adversary of the F-1 was combustion instability. Glushko was correct about the negative consequences of constructing a larger engine, but NASA was determined to solve it. The solution had more to do with acoustics than rocket science. The engineers built in a series of precisely tuned baffles and resonators into the engine's structure that would regulate and direct the flow of exhaust gas in the same manner that the precisely carved wooden body of a violin transforms vibration from the strings into a beautiful musical tone. The body of the F-1 transformed explosive chaos into raw, concentrated power. Another extremely important but frequently overlooked innovation on the Saturn V was the J-2 engine. This powered the rocket's second and third stages after separation from the colossal booster segment. The J-2s were fueled by a combination of cryogenic liquid hydrogen and liquid oxygen, the identical propellant mixture that our old friend Konstantin proposed back in 1903 as the ideal rocket fuel, and he was accurate. The J-2 was not a high-thrust monster like the F-1, but it was ultra-high efficiency. Once the Saturn V had built momentum and cleared the Earth's atmosphere, these 2 hydrogen-powered upper stages would supply all of the energy required for an express trip from Earth orbit to the moon. Of course, the Saturn V rocket was highly successful in its objective of landing men on the moon, but its career was brief. By 1972, the F-1 was retired, and nothing comparable to it would ever be constructed again. However, the hydrogen-fueled innovations of the J-2 would endure in NASA's next major project, the Space Shuttle. Getting a space shuttle into orbit was no simple task. While conventional rockets like the R-7 and the Saturn V had commenced on the ground with enormous boosters beneath, the portion of the rocket that actually went into space was relatively small. With the shuttle project, NASA was attempting to get a very large spaceplane into orbit, and it had to be capable of reaching high altitudes to deploy significant important payloads like the Hubble Space Telescope. The shuttle needed a combination of high thrust and high efficiency, and to achieve that, the rocket lifted off under the power of 2 very different engine types. Strapped to the sides were 2 solid rocket boosters, the most primitive of all rocket engines. This concept traces all the way back to China and the Song dynasty. It's simply a large tube filled with flammable powder. They place a cap on one end and a nozzle on the other. Then you ignite it and hope for the best. Inside the shuttle orbiter itself, there was a significantly more modern propulsion system at work, the RS-25 hydrogen-fueled rocket engine. We are now entering a post-von Braun era of NASA, and this new engine will become the American workhorse for the next 3 decades of human spaceflight. There were several challenges to overcome with the RS-25. It had to operate both at sea level on Earth and in the vacuum of space. It needed a throttle control to manage the velocity of the winged orbiter as it ascended through the atmosphere. Unlike a straight-pointed rocket, you can't simply go full force when you're essentially flying a plane straight upward. And most importantly, the rocket engine needed to be reusable for the first time. While every other rocket booster ever manufactured had simply been dropped from space to plunge into the ocean or crash into a desert, the shuttle would come home for a landing, so its engines needed to be capable of flying multiple times without requiring extensive maintenance. This is where hydrogen fuel truly excels. When you burn kerosene, you end up with a lot of soot as a byproduct, and that doesn't matter in an engine that's going to be dropped into the ocean. But in a reusable rocket engine, you don't want it to return full of grime that needs to be cleaned out. Hydrogen burns cleanly. The only byproduct of combusting hydrogen and oxygen is water vapor. This also permitted the RS-25 to implement the very first closed-cycle gas generator. On previous engine designs like the Soviet RD-107 and the American F-1, the gas generator that powered the fuel turbopump had an open cycle, meaning that the exhaust gas powering the turbine is discarded overboard. This is done for simplicity, and it's also done because soot from the gas generator would rapidly obstruct the system and the engine would fail. So with clean-burning hydrogen, you don't have to sacrifice 3% of your fuel just to run the pumps. That exhaust energy can now be contained in a closed-loop system. This maximizes efficiency and increases the combustion pressure inside the engine, which increases the thrust-to-weight ratio. This keeps the RS-25 small enough to fit 3 of them into the tail of the shuttle orbiter. There was also sufficient room in the tail section to install a hydraulic gimbal system that could alter the angle of each engine individually. By angling the thrust from the engine, you obtain a higher level of steering control as the orbiter ascends. It would be decades before rocket scientists could discover a way to evolve the rocket engine beyond what NASA had accomplished with the RS-25, and that is where SpaceX enters with the Starship Super Heavy rocket and its Raptor engines. Raptor would have to be an exceptional engine in order to deliver on Elon Musk's grand vision for Starship. The rocket would need to transport massive amounts of crew and cargo into space, then fly to the planet Mars, land on Mars, refuel, and then fly all the way back to the surface of the Earth and land again. To accomplish this, the Raptor would need to satisfy every requirement all at once. The raw power of the F-1, the reliability of the RD-107, the efficiency of the RS-25, and all of that capability would have to be packaged in a compact design that would allow for mass production on a scale that the rocket industry had never witnessed before. NASA built 5 functional space shuttle orbiters, each with 3 engines. SpaceX wants to build 1,000 starships with up to 9 engines each, and in addition to that would be hundreds of super heavy boosters, each one carrying 33 engines of their own. SpaceX engineers advanced the Raptor by introducing the first ever full-flow staged combustion cycle engine. So just like the shuttle, it uses a closed-cycle gas generator to power the fuel turbopump, except Raptor has 2 gas generators, and each one powers a separate turbopump, one for fuel and the second for oxygen. With the twin turbopump setup, Raptor is able to drive even more pressure into the combustion chamber than ever before. The F-1 engine generated around 100 bar of pressure in its combustion chamber. Using one open-cycle gas generator, that means 100 times more air pressure than what we experience on the Earth at sea level. The RS-25 brought that up over 200 bar of pressure with a closed-cycle gas generator. Then the SpaceX Raptor version 2, with dual closed-cycle gas generators, has brought that up to over 300 bar of chamber pressure, which is equivalent to being 3,000 meters deep underwater. In addition to that, SpaceX introduced a new fuel source, methane. The reason that SpaceX moved away from hydrogen fuel is because there is no natural source of pure hydrogen. It's a very reactive atom, so it's always going to be found attached to another element, so you have to expend a lot of energy to separate it. Typically, we do that with water, We break it apart into hydrogen and oxygen atoms using a large amount of electricity. Methane is what happens when 4 hydrogen atoms bond to 1 carbon atom, CH4. So it's very similar to pure hydrogen. And there are vast amounts of methane gas trapped beneath the surface of the Earth. We know it better as natural gas. Millions of people use it for heating and cooking every day. All you have to do is make natural gas so cold that it converts into a liquid, and you obtain a very powerful rocket fuel. You can also produce methane on the planet Mars. The atmosphere is full of carbon, and the surface is full of frozen water. Combining the two together will provide you with enough methane and oxygen to refuel a starship and fly it home to Earth. So with each evolution of the rocket engine, there was always a driving factor. Sometimes that was manufacturing more powerful weapons to win a war. In other times, it was done to win a space race and land on the moon. In the modern day, rocket engines are evolving to help spread human life to other planets of the solar system. But at the core of even the most advanced rocket science, we are still just igniting fires to push things forward. This is still primitive technology, and we have so much room left to grow.